You type a few words, a teacher at a chalkboard, a red bicycle leaning on a wall, and a moment later a photo appears that has never existed anywhere on Earth. So here is the question nobody asks. How? Most people picture the machine painting like an artist filling in a canvas stroke by stroke, left to right. That is almost the exact opposite of what happens. The machine starts from a screen of pure noise, the kind of TV static you get with no signal, and it removes the static. Step by step it asks one strange question, over and over. What here is noise? It peels that noise away, and hidden underneath, the picture you asked for slowly comes into focus. Creating an image, it turns out, is the reverse of destroying one. That family of methods is called diffusion, and it is the engine behind almost every text-to-image tool you have heard of. So let us open the engine up and see exactly how static becomes a bicycle. A diffusion model is a neural network that learns to make images by reversing a noising process. The idea sounds almost too simple. Take a real photo, add a little noise, add a little more. Keep going until the photo is nothing but random static with no trace of the original left. That is the destroying half, and here is the key. Destroying needs no intelligence at all. Sprinkling random noise on a picture is just a fixed mathematical recipe. The hard part, the only part the machine actually learns, is the reverse, undoing it. The model is trained to look at a noisy image and figure out what noise is in it, so that noise can be subtracted and the image gets a little cleaner. Do that enough times, and you can start from total static and walk backwards all the way to a clean image. Train it on a vast collection of pictures, and it does not just clean up one photo. It learns to conjure brand new ones out of noise alone. Here is why this is bigger than pretty pictures. The trick, learn to undo noise, then run it backwards from pure static, is not really about images. The exact same machinery now generates video, where each frame is denoised together. It generates audio and music. It builds three-dimensional shapes, and it even designs candidate molecules and proteins for medicine. Swap what you train it on, and the same denoising loop creates in a new world. So when you understand diffusion, you are not learning one app. You are learning a general engine for making things. And there is a second deep idea hiding here. Generating an image and steering that generation toward your words are two separate mechanisms. One part dreams up an image. A different part nudges that dream toward a teacher, or a bicycle, or a sunset. Capability and the control of capability are pulled apart into different knobs. That separation, as we will see, is what turns these tools from slot machines into instruments you can actually direct. Before the mechanism, look at what one trained model can do, because it is more than the headline. The headline, of course, is text to image. Words in, a coherent new picture out. But because the machine only knows one move, remove noise from a partly noisy input, you get a whole family of abilities for free, with no new model. Start the denoising from a real photo with just some noise added, and you get image to image, reworking a picture into a new style. Mask out one region, add noise only there and denoise just that patch, and you get inpainting, replacing part of a photo seamlessly, or outpainting, extending a picture beyond its edges. Point it at a low-detail image and it can denoise upward into a higher resolution. And the steering accepts more than words. You can guide it with a rough sketch, a stick figure pose, a depth map, or a layout, so the output follows a structure you hand it. One trained network, many jobs, all the same underlying move. Now the heart of it. We will build the machine in pieces, starting with the easy half, destroying. Take a clean image. In the original models, this happened over a long ladder of steps, around 1,000 of them, though newer models use far fewer. At each step you add a tiny bit of Gaussian noise, a small random fuzz, following a fixed schedule that starts gentle and grows. Each noisier version depends only on the one just before it, a chain where every link adds a little more chaos. Climb the whole ladder, and the picture is gone, indistinguishable from pure random static. And here is the elegant shortcut that makes all of this affordable. You do not have to crawl up the ladder one rung at a time. There is a formula that jumps straight to any noise level in a single move. blending the clean image with a known amount of known noise. That matters enormously, because every one of those noisy versions, paired with the exact noise that was added, is a free training example. Real photos plus random noise give the machine an endless supply of homework, with the answers already attached. Now the learned half, the reverse. The machine is shown one of those noisy images and the time step, how far up the noise ladder it sits, and it is asked a single question. What is the noise in this picture? It outputs a guess at that noise. The standard name for this is noise prediction. Then we check the answer because we know the true noise we added, and we penalize the gap with a stunningly simple error measure. The closer its guess, the better its score. That is the entire training objective. Show a noisy image, ask it to name the noise, correct it. Do that across millions of images and millions of noise levels, and the network gets very good at spotting noise at any stage of decay. To generate a fresh image, we run that backwards. Start from pure static. Ask the network what the noise is. Subtract a scaled slice of it to get a slightly cleaner image. Ask again. Subtract again. And here is the part to hold on to. It is one single network, called over and over, dozens of times, each call gently cleaning what the last one left behind. This is the single most important thing to get right, because nearly every casual explanation gets it wrong. The model does not paint pixels. It does not predict the next pixel the way a language model predicts the next word, filling the picture in some order. It does not produce the finished image in one shot. At every step it answers only that one question: what noise is in this image right now, and a bit of that noise gets subtracted. The whole picture refines together, in parallel, gradually, over many passes, like a blurry photo developing all at once rather than being drawn corner by corner. And why predict the noise instead of predicting the clean image directly? The researchers tried both, and aiming at the noise simply worked better. There is a subtlety worth naming, so you are not surprised later. Some variants do predict the clean image, or a related quantity called velocity, instead of the raw noise. But predicting the noise is the canonical default, the one to picture. The model is a noise detector, run on a loop, not a painter. But wait, why should removing noise again and again ever produce a coherent image rather than just smoother mush? Here is the intuition, and it is beautiful. Imagine a vast landscape where every possible image is a location, and the height of the land is how realistic that image looks. Real, natural-looking photos sit down in the deep valleys. Random noise sits up on the barren peaks. When the network predicts the noise to remove, it is mathematically the same as pointing downhill, toward more realistic, more image-like territory. Researchers call that downhill direction the score, the gradient toward higher probability. So each denoising step is one small step downhill, toward the valley of plausible images. Run enough steps and your starting blob of static rolls down into a coherent picture, simply because every step nudged it toward looking more real. This is also why you will hear two phrases used almost interchangeably: diffusion models and score-based models. A landmark result showed they are two views of the same underlying process, not two different things. What is the network that does all this denoising? The first diffusion models used a shape called a U-net, an encoder-decoder that squeezes the image down to grasp the big picture, then expands it back up to restore fine detail, with shortcut connections carrying detail across the gap. Newer, larger models swap that for a transformer, the same attention-based architecture behind modern language models, because it scales up more gracefully with data and compute. But notice, the mechanism, predict the noise and remove it, never changes. Only the engine under the hood gets bigger, and there is a close cousin worth a brief, honest mention. Some of the newest systems use a related formulation called flow matching or rectified flow. Instead of that long, wandering, random noise ladder, it learns the most direct path, roughly a straight line from noise to image, which lets it get there in fewer steps. It is a sibling of classic diffusion, sharing the same core spirit. So if you hear that a recent model is not strictly a diffusion model, but a flow-matching one, now you know it is a close relative, not a different planet. So far the machine makes images, but random ones. How do your words steer it toward a red bicycle? In two parts. First, your prompt is fed to a separate model called a text encoder, which turns the sentence into a list of numbers, a vector. The clever bit is the kind of encoder used, often a model from the clip family, which was trained on hundreds of millions of image and caption pairs until matching pictures and words land at nearly the same spot in a shared space. That shared space is the secret. It is the reason a string of text can describe a target image at all, because in that space, the words red bicycle sit right next to actual photos of red bicycles. Second, that text vector is injected into the denoiser at every single step through a mechanism called cross-attention. Picture each patch of the noisy image glancing up at the prompt words and asking, "Which of you matters to me?" The prompt is not applied once at the end. It whispers into all several dozen denoising steps, biasing what noise gets removed so the emerging image drifts steadily toward your words. Two more pieces complete the core. First, the prompt strength dial with the standard name classifier-free guidance. At each step the machine actually denoises twice, once while listening to your prompt and once while ignoring it completely, since it was also trained to run blind. Then it exaggerates the difference, pushing away from the blind version and toward the prompted one. A scale knob sets how hard. Turn it up and the image clings tightly to your words, crisper but less varied, and pushed too far it can look oversaturated and fried. Turn it down and it wanders, more creative but looser to the prompt. Crucially, no separate judge is grading the picture. The model just compares its own prompted and unprompted guesses, which is why it is called classifier-free. Second, the speed trick that put this on ordinary computers, latent diffusion. Denoising every raw pixel is wildly expensive. So the image is first compressed by an autoencoder into a much smaller grid of numbers, a learned, meaningful summary, not just a tiny thumbnail. All the denoising happens in that compact space, then a decoder expands the finished result back into full pixels. That one move is why this can run on a laptop. One last efficiency, then we assemble the whole machine. You might think you need every rung of that 1,000-step ladder to generate. You do not. Clever recipes for taking the steps with names like DDIM and other fast solvers reach comparable quality in roughly 20 to 50 steps, and distilled versions push that down to just a handful. The trained model is unchanged. Only the sampler, the recipe for how big a step to take, gets smarter. So here is the entire pipeline in one breath. Your prompt goes into a text encoder, becoming a vector. You start from a small grid of random noise. The denoising network predicts the noise at this step, conditioned on your words through cross-attention, sharpened by guidance. A slice of noise is subtracted. Repeat that around 50 times. A decoder expands the clean little grid back into full-resolution pixels, and a brand new image steered by your sentence appears. Every knob you will ever touch in one of these tools maps onto a piece of that pipeline. Where does diffusion sit among the alternatives? Before it, the leading image generators were GANs, where two networks fight, one forging images and one trying to spot fakes. GANs could be brilliant but were notoriously unstable to train and hard to steer, and for general text-to-image, diffusion largely overtook them by being more stable and more controllable. So diffusion is the successor to GANs, not a synonym for them. There is also a genuinely different approach worth separating clearly. Some newer image systems are autoregressive, building the picture as a sequence of little tokens predicted one after another, exactly like a language model predicting words. That is not denoising at all. It is the next token machinery applied to images, and some native multimodal models work that way or as hybrids. So when you meet an image generator, it is worth knowing which family it belongs to. Diffusion and its flow-matching cousin refine the whole image in parallel over many steps. The autoregressive ones predict image pieces one at a time. Same goal, very different engines. How do you actually use one and what does it cost? 3 routes. Open weights models you can download and run on your own machine, free, the real payoff of latent diffusion. Polished apps you pay a subscription for, or an interface you call by the image. The mechanism is identical across all 3. The knobs you will turn map straight to what we just built. The prompt, plus a negative prompt for things to avoid, which is simply a second direction to steer away from. The guidance scale, your prompt strength dial. The number of steps, trading speed for quality. And the seed, the specific starting static where the same seed and prompt reproduce the same image, handy for iterating. The cost is mostly compute, roughly steps times resolution times those guidance passes, which is exactly why fewer steps and the compressed latent space were such a big deal. Now the honest limits. Early diffusion models, back in the first couple of years, often mangled hands into extra fingers and turned any lettering into gibberish. Because hands are anatomically complex and humans are exquisitely sensitive to them. And exact text needs precise long-range character order that those early networks handled poorly. Newer models, with bigger text encoders and transformer backbones, do both far better, so treat the old hands-in text jokes as history, not as how these tools behave today. A few more honest caveats. Precise composition can still trip these models, things like 3 red cubes to the left of 2 blue spheres, with exact counts and positions, because the steering is a soft nudge, not a strict layout engine, though better encoders and structural guidance help. There is also a real ethical fault line. These models can occasionally regurgitate near copies of their training images. Researchers have extracted recognizable training pictures out of a public model and found diffusion models leak more than twice as much training data as GANs did, and the licensing of the web scrape data they learn from is genuinely contested. And let us clear up the common myths. It does not search a database and collage existing images. It learned the overall shape of what real images look like and samples a fresh one, with that rare memorization being the exception, not the method. Latent space is not a low-res thumbnail. It is a learned, compressed summary. Guidance is not a critic grading the picture. It is the model comparing its own prompted and blind guesses. And not all image AIs are diffusion. GANs came before, and the autoregressive token models are a different engine entirely. So step back and look at the whole idea. The deepest lesson of diffusion is almost philosophical. You do not need to know how to build a complex thing in one perfect shot if you can learn to undo its gradual destruction and then run that undoing backwards. Learn to denoise, then iterate from pure noise and you can create. That single move now makes images and video and sound and 3-dimensional shapes and candidate molecules. The same loop in a new world. And the practical lesson for using any of these tools is the separation we kept meeting. Your prompt, a point in that shared space of words and pictures, decides what gets made. The guidance dial decides how literally. The seed decides which particular version. Generating and steering the generation are different knobs you can turn independently. So here is the whole thing in one line. The machine never painted your picture left to right. It started from pure static and patiently removed everything that was not the image. A single network asking, dozens of times, what here is noise, steered all the while by your words. And that one reversal, turning destruction into creation, is now how machines imagine.